Okay, good morning, everybody. This is College Algebra. A couple of announcements. Doug, you're online. I don't know if you remember this, but I did send an email out sometime, I think, over the weekend that we have a factoring contest in North Harris every fall, and that's going to be today. I forgot to announce it during lecture on Monday, which I feel bad about doing. But I did send an email out. I didn't even know about the contest until when they were going to have it until last week. But it is going to be this afternoon at 3:30. I'm going to send an email out about this to everybody as soon as I'm done lecturing today. Also to remind everybody to 3:30 on the North Harris campus at Winship 207. You have to have a student ID. I will assign or give a little bit of extra credit on exam 3 for students of mine that participate. And so if you're interested, there is a review on my Google page also for factoring. And it's kind of late to do that now because it's just this afternoon. But, it's possible that some of you who are watching this video this morning may want to just go and look at that review for an hour or two and then go try your hand at the contest. The worst that could happen is you go and get a little bit of extra credit, and the best that can happen is that you get some cash prizes also. So there's nothing negative that can happen by going to the factoring contest. Let's see, the exam 3 review. I want to make sure that everybody knows that that is now online on my Google page, and so you can now go and start looking at exam 3 review and start getting some ideas of what's going to be on exam 3 and start getting ready for that. The testing window for exam 3 runs from November the 30th through December the 5th. And, let me point out also that the final exam window opens December the 7th. So, the final exam comes right after exam 3. The turnaround on that's going to be very fast. As always, let me remind you that I do have online office hours. Don't hesitate to come by for help during my online office hours. I will be happy to help you out. I'll be online again this evening from 8 to 9. And then I have some hours in this class tomorrow during the day also. And then I'm also online Sunday evenings, 7:30 to 9 o'clock. So please come by for help if you have questions. WebAssign homework. You have some WebAssign homework that's gradually coming due. The next group of homework that's due is on November 21st. Section 6.3, 6.4, and 6.5. And then 6.6 and 7.3, 6.6 is what we're covering right now, is not due until December the 6th, until towards the very end of the semester. So you still have some time to do that homework. All right. So today, or last time actually, we solved exponential equations and looked at different types of exponential equations. Where I referred to them as type 1 exponential equations and type 2 exponential equations, and how you use properties of exponents to solve type 1, and type 2 that you use logarithms to solve. Today we're going to look at equations that involve logarithms and how to solve logarithm equations. Also, like I said, in section 6.6 of your book. So if there are no questions, and Doug, do you have a question before I actually get started?
No, sir, I'm good.
Okay. Then from last time, first let's talk about that one more time as we leave that. From last time, we have exponential equations that involve the exponential expressions, and solving those. And so remember, I looked at two types. I looked at type 1, where we use properties of exponents. To solve those. So an example of that would be a problem like this. Let's say you have 3 to the 4x plus 1 equals 1 over 9 to the x minus 5. Okay, so this would be an example of a type 1 exponential equation, and the reason why it's type 1 is that all the bases are powers of the same number. In this case, 3 and 9 are both powers of 3. Right? 3 is 3 to the first power, and 9 is 3 to the second power. And so since they're all powers of 3, that means we can use properties of exponents to solve this equation. Now 3 to the 4x plus 1 we would just leave alone for now, but the 9 we'd write as 3 squared, like that. And then take 1 over 3 squared and write it as 3 to the negative 2. Remember, the whole idea when you're solving type 1 exponential equations is that you want to write the equation in the form b raised to the x power equals b raised to the y power. Right? And if you can get the bases to be the same on both sides of the equation, then you can just equate the exponent. So you're using, that's sometimes called the one-to-one property for exponential expressions. So we're close to that form right now. We just multiply exponents on the right side of the equation. Be careful that you're multiplying exponents there. So that's the distributive property. And so you have negative 2x plus 10. So this is negative 2x plus 10 right here. Really common to see students multiply the negative 2 by the x, but forget to multiply it by the 5. So be really careful about that. And see, this is the form we're looking for. This is the bases are the same. That's this form right here. And so if the bases are the same on both sides of the equal sign, that means that the exponents have to be equal to each other. And so we set the exponents equal to each other and then solve that equation. So if you add 2x, you get 6x plus 1 equals 10. I subtract 1, I get 6x equals 9. Divide by 6, I get x is 9 over 6, or 3 over 2. And so 3/2 would be our solution. As always, I went through and spent a lot of time checking these in lecture on Monday, and never a bad idea to check these solutions. I think it gives you good practice for one thing, but then it also guarantees that you're right. So that's a good thing to be able to do. So notice what I'm doing here is every place, I take the original equation. Here's my original equation right here, and I take that in every place I see an x, I'm going to substitute 3/2. So on the left side of the equation, you have 3, the 2 and the 4 cancel and leave you the 2, so you get 3 to the 6 plus 1, or 3 to the 7th power, equals, and then on the other side of the equation, you get 1/9, and then 3/2 minus 5, that's 3/2 minus 5 over 1, or 3/2 minus 10 over 2, and so that's negative 7/2 over there, because you have 3/2 minus 10/2 is negative 7/2. And then, well, you get that 1/9 to the negative 7/2 would be the same thing as 9 to the positive 7/2. Remember, if you just change the sign of the exponent, you're flipping the fraction. So I changed the sign of the exponent from negative 7/2 to positive 7/2. I flipped the 1/9 to 9 over 1. And then finally, what you could do here is you could rewrite 9 as 3 squared. And then you multiply those exponents. So what happens? You have 2 times 7/2 is 7, and you end up with 3 to the 7th equals 3 to the 7th. So it can be a challenge just to check these solutions, but it does give you good practice at dealing with exponents also. So I think checking these is a good thing to do. All right, so that was a type 1. That's another example of a type 1 exponential equation. A type 2 exponential equation is one where you had to use logarithms to solve the equation. So now you're using properties of logarithms. Right? In other words, there's no way to rewrite both sides so that the bases are the same. And so your only choice there is to try to use logarithms to solve the equation. So let's see, as an example there, let's look at an equation that looks like this one right here. Let's say we have 40 e to the 5x minus 3 plus 80 equals, let's say, 200. All right? So this is an example of a type 2 exponential equation. And in a type 2 exponential equation, you want to write this at the end. You want to get this equation in the form just b raised to some power equals a constant. Right? That's what you're looking for. And then you take the log of both sides of the equation. Right? Then you take the log of both sides. And remember here what you're doing is you're taking advantage of this property that if two numbers are equal, then their logarithms have to be equal also. And now I just wrote log base 10 there, but it could be any base you wanted to. So I'll just say log base little a right there. You use any base logarithm that you want. All right, so in this problem, the first thing we need to do is get this exponential expression by itself. So we subtract 80 from both sides. So you have 40 e to the 5x minus 3 equals 120. And then you have to divide both sides by 40 to get rid of the 40 there. And now you have e to the 5x minus 3 equals 3. And that's what we're looking for, is we're looking for an exponential expression equals a constant. And so now you take the log of both sides, but since the base is e on the exponential expression, you need to use ln on both sides. You need to use the logarithm base e. That'll make the problem much easier to do at the end. So you take the log of both sides of the equation, and I use log base e on both sides. Right? And then I use the power rule for logarithms, and I bring the 5x minus 3 down in front as a factor. Remember, that's the power rule for logs right there. So you bring the power down in front. So that leaves you with the natural log of e equals the natural log of 3. And then right here, this is why you use natural log, is because the natural log of e is equal to 1. Because remember, that's the power that you raise e to get e. Remember, the base on this logarithm is e. And so it's the power that you raise e to get e. And so this factor goes away. That's just a 1 right there. And so that makes it easier at the end. And so you get 5x minus 3 equals the natural log of 3. Add 3 to both sides to solve for x. I put the 3 in front of the logarithm so that I don't get confused as to what I'm taking the log of. And then I divide both sides by 5. And I've got the solution to the equation. In WebAssign, WebAssign is going to ask for this form right here, probably. Just so you know. But on the exam, I'm going to ask for a decimal approximation for this. And so the decimal approximation, in this case, you'd have to enter this as put parentheses around the numerator. And this is the way it would look in your calculator if you're using a graphing calculator to enter this. If you're using a scientific calculator, unfortunately, it's not going to look like that. Scientific calculator, you kind of have to enter things differently because of the way a scientific calculator frequently works. So, but on a graphing calculator, you can enter it pretty much the way you write it. And remember, I talked about this in the last lecture also, is if you're going to enter this on a graphing calculator, I would write it out off to the side on your paper, just like I just did right there, so you can see it written out, and then you can translate it to your calculator. I think that's definitely a thing that you need to do. I will probably ask you to round to 3 decimal places. So this is the answer that I get on my calculator, 0.8197224577. So if I ask you to round this to 3 decimal places. The third decimal place is a 9 here, but the number past it's a 7, so it's bigger than 5, so you're going to round that 9 up. And so to 3 decimal places, this would be 0.820. I am not going to make a big deal about how rounding. If there's a slight mistake in the rounding, you've got all this big complicated problem that you're solving. I'm not going to make a big deal about just making a really tiny rounding mistake at the end of a problem. But you should be careful about that also when you're doing that. All right. So that was kind of going back and doing a rehash on log or on exponential equations. And so now we're going to look at log equations. And in log equations, I kind of separate those into type 1 and type 2 log equations also, just like I did exponential equations, kind of a different way of dividing them up. But type 1 logarithm equations are logarithms where you can logarithm equations where you can write the equation so that it looks like this right here. Just a logarithm equals a constant. Because if you can write the equation as a logarithm equals a constant, then you can just rewrite in exponential form right? If you rewrite it in exponential form, then you can solve the equation. Now, type 2 logarithm equations, you have a different approach. Type 2 logarithm equations look like this, where you have a logarithm of something, like we'll say capital A, equals logarithm base A of something else. Let's say capital B. So if you have a logarithm equals a logarithm, if that's the way you're writing the equation, then you can take advantage of the fact that logarithms are one-to-one and say that if their logarithms are equal, these two numbers have to be equal. And so you can just set A equals to B and then solve the equation. Right, and you base whether you have a type 1 or a type 2 logarithm equation pretty much based on whether you have all the terms are logarithm terms, or if there's some term in the equation that's not a logarithm term, if it's just a constant. If you have a term in the log equation that's a constant, then it's a type 1. But if they're all logarithms, then you're going to work it as a type 2 log equation. All right? So let's look at some examples of log equations. And I'm going to start out by taking some problems out of your textbook and working some of those. So I'm going to start off with problem 32. By the way, this is on page 535 of your textbook, section 6.6, and this is problem number 32. You have this equation. You have negative 8 log base 9 of x equals 16. Negative 8 log base 9 of x is equal to 16. Okay, so you see that there's a term in there that's not a logarithm term. That 16 is not a logarithm. So this is probably going to be a type 1 logarithm equation, in which case you're going to want to get the logarithm by itself equals a constant. Now, the logarithm is not quite by itself like it is. You need to divide both sides by negative 8 to get the logarithm by itself. So you have log base 9 of x is equal to negative 2. See, and now it's in that form. Now it's in the form logarithm, like I've got written at the top, logarithm of something equals a constant, right? And so now what we do is we write this logarithm in exponential form to solve the equation. So in exponential form, remember this would be, remember the logarithm is always equal to the exponent. So that negative 2 is an exponent. And the base on the logarithm and the base on the exponential expression are always the same. And so this is 9 raised to the negative 2 power equals x. And see, boom, you solved the equation. You got it. Now don't leave it as 9 to the negative 2. Rewrite that as 1 over 9 to the positive 2, or 1 over 81. And so 1 over 81 would be the solution to this equation. 1 over 81. Now, you can certainly check to see that this is a true statement. You know, like I was checking exponential equations last time and earlier in class today. There's no reason why you can't check these. And again, the checks can sometimes be challenging to go through in these problems. So you have negative 8 log base 9 of 1 over 81 is equal to 16, right? That's what we're trying to check here. And that logarithm base 9 of 81 is what you've got to deal with. You have to work with that number right there. So if you kind of work on that off to the side, there's a couple ways you could look at that. But one way you could look at log base 9 of 1 over 81 is you could rewrite 81 as 9 squared. So this is log base 9 of 1 over 9 squared. And so that would be log base 9 of 9 to the negative 2. And then you could bring the negative 2 down in front, and then this would be log base 9 of 9. And the reason why I do that is because log base 9 of 9 is equal to 1, because it's the power you raise 9 to get 9. So notice this is just negative 2 times 1, or negative 2. So what we just calculated off to the side is that this logarithm has the value negative 2. And so what do we get there? We get negative 8 times negative 2 equals 16, and boom, that's true. Like I said, it gives you good practice of working with logarithms, but it can be challenging to check these. There's absolutely no question about that. And so sometimes you may have a little bit of a struggling just with the check to go through some of these problems. Now, that can be tough to do. All right, so let's. So that was a type 1 logarithm equation. Now, logarithm equations come in all sorts of different forms, so be prepared for that also. This is number 34, that they're going to look all sorts of different ways, and you just have to learn to adapt to the different forms that they're written in. Don't think they're all going to look the same. This is 2 log of 8n plus 4 plus 6 is equal to 10. So once again, we have these constant terms in there that are not logarithms, so that would suggest that this is a type 1 logarithm equation. So that means we want to get the logarithm by itself equals a constant. So in this problem, I'm going to subtract 6 from both sides, right? Because I want to get that logarithm by itself. So this is 2 log of 8n plus 4 equals 4. And then this looks similar to the problem we did on the last screen. Divide both sides by 2 to get the logarithm by itself. So this is the log of 8n plus 4 equals 2. All right, so now that's the form you want. You want a logarithm equals a constant. Now you have to be careful here. What's the base on this logarithm? Remember, when the base is not written, this is understood to be log base 10. Right? This is just a shorthand form for this statement right here. This is called the common logarithm, remember. So the exponential form, remember that's what you're going to try to do at this point, is write this in exponential form. So the exponential form for this logarithm equation would be 10 to the second power equals 8n plus 4. Right? 10 to the second power. Remember, the logarithm is equal to the exponent. Right? So this logarithm is equal to 2, so 2 has to be the exponent. The base on the exponential expression and the base on the logarithm are the same. So let's see. So 10 squared is 100 equals 8n plus 4. Subtract 4 and you get 96 equals 8n. And then finally divide by 8. And when you divide by 8 on both sides, you get n is 12. And so 12 would be our solution to this equation. All right, if you wanted to check that. So if we're going to check n equals 12, then I go to my original equation, and every place I see an n, I substitute 12. And there's just one place where there's an n, like so. And so you get 2 times log of 96 plus 4 plus 6 equals 10. So 96 plus 4 is 100. So this is the log of 100 plus 6 equals 10. And then that's log base 10. So that's the power you raise 10 to get 100, which is 2. So this is 2 times 2 plus 6 equals 10. And that is true. 4 plus 10 4 plus 6 is 10. And so it definitely checks. Okay, so we're doing good here. The next problem I want to look at is I'm just kind of skipping around a little bit here and looking at different kinds of problems that you're going to encounter. So the next problem I want to look at is number 54, which looks simple enough, but there's definitely a complication here. So on number 54, you have the natural log of x minus 5 equals 1. Natural log of x minus 5 is equal to 1. All right, so on this problem, it is already a logarithm equals a constant. This is a type 1 log equation. There's that constant term, and it's already in the form a logarithm equals a constant. So we're going to write this in exponential form here. Now remember, the natural log is really a logarithm base e. So if you get confused on how to write this in exponential form, then just write this as logarithm base e of x minus 5, because that ln, remember, is just a shorthand for that equation right there, or that statement. So write that in exponential form, that expression right there, that equation. So in exponential form, that would be e to the first power equals x minus 5. And so that would be your exponential form, and you could solve it for x. I would just leave the e alone and just leave it as e. Remember, e is a constant. Remember, e is approximately equal to 2.718. So this would be e plus 5 equals x. And on WebAssign is probably going to ask you just to write the answer like that, as e plus 5. That's the exact answer like that. On the exam, I'm going to ask you for a decimal approximation for that. So the decimal approximation here would simply be that x is approximately 2.718 plus 5. Don't even need a calculator if you know the decimal approximation for e. And so you get about 7.718. And so that's our solution. That's what I would want to see on the exam, 7.718, because I'm going to want to see a decimal approximation for this. All right. You could certainly check this problem. I mean, despite the way the answer is written, that you could check it. And actually, the check works out relatively easily here, because you have the natural log of x minus 5, but x is e plus 5. So you have e plus 5 minus 5 equals 1. And so notice the 5's add to give 0. You're just left with the natural log of e equals 1. And remember, the natural log of e is equal to 1. And so this does check. Right? E plus 5 is the solution to this equation. All right. So far we've looked at all type 1 logarithm equations. Let's look at something that is a type 2 logarithm equation. So let's look at, start off with something relatively easy like number 36. Number 36, you have the natural log of 10 minus 3x equals the natural log of negative 4x. So you see in this problem, there are no constant terms. All the terms are logarithms. Everything is a logarithm. And so when everything is a logarithm, this is a type 2 log equation. Right? All the terms are logarithm equations. And remember what I mentioned earlier is that in a type 2 logarithm equation, you've got logarithm base b of capital A equals logarithm base b of capital B. And that's what you're looking for. And when you get the the equation to look like that, then you can just say that a is equal to b. So moral to the story there, if you can get logarithm equals a logarithm, then just set the two expressions equal to each other. See, and notice that's what our problem's already in that form. It's a logarithm equals a logarithm. It's a natural log equals a natural log. And so what has to be true here? 10 minus 3x has to be equal to negative 4x. There's no other way that this could be true. And so you just solve this equation for x. So let's see, I add 3x to both sides. And so you get 10 equals negative x. And so you get that x is negative 10, right? Just multiply both sides by negative 1 and you get x is negative 10. Now I do want to warn you that sometimes you'll end up with an equation that does not have a solution. That's definitely possible that you can end up with a logarithm that when you try to check your solutions, when you have a logarithm equation, when you try to check your solutions, that you come up with something that's not really a solution. You can get extraneous solutions with logarithm equations. Remember, and the way that turns out, by the way, is remember that you can't take the log of a negative number. Right? If you get the log of a negative number, that is undefined. Right? It has no meaning. It's a meaningless expression. And sometimes you can come up with a solution to an equation that gives you the log of a negative number, in which case you have to throw that solution out of the equation. That can happen. Now, it doesn't happen in this problem, but I did want to point that out. It hasn't happened in any of the problems we've talked about yet, but it can definitely happen. So if I'm going to check this, let's see, I'm going to enter this correctly. So you have the natural log of 10 minus 3 times negative 10. Right, every place I see an x, I am putting negative 10. Right, so I substitute negative 10 in every place I see an x. And so on the left side, I get the natural log of 10 plus 30, or the natural log of 40. And on the right side, sure enough, that's exactly what you have, the natural log of 40. Negative 4 times negative 10. And so this definitely checks. Natural log of 40 is definitely equal to the natural log of 40. Okay? All right, let's look at problem number 44. So in problem 44, you have logarithm of x plus 12 equals logarithm of x plus log of 12. Now remember, these are all common logarithms. So these are all base 10 logarithms. Now notice this equation is not in the form logarithm equals a logarithm. Because on the right side of the equation, you have two logarithms that are added together. And so what you have to do here, in order to get this as, if you want to put it in the form of logarithm equals a logarithm, right, that's what you're trying to do, is put in the form a logarithm, whatever the base doesn't matter, equals a logarithm. Then what you have to do here is on the right side of the equation, right here, you have to combine those two logarithms. And remember, you do have a way of doing that. You have a property of logarithms that says if you have an addition problem, that you can use the product rule for logarithms to combine those, right? Because it's addition. And so what you end up with here is you end up with log of x plus 12 equals log of x times 12, right? The product rule, or just the log of 12x, right? So remember, you can combine an addition problem where you're adding two logarithms. You can add two logarithms by using the product rule. And so now notice you've now got the equation in the form logarithm equals a logarithm. And so you can now set these two, use the one-to-one property. You can set these two numbers equal to each other, the x plus 12 and the 12x, and you can solve this for x. You just subtract x from both sides. And you get 12 equals 11x. And then divide by 11, and you get 12 elevenths is equal to x. And so that is going to be your solution. You know, you can be guaranteed that when you if when you try to check these equations, that if you don't get the log of a negative number, then it's not going to be an extraneous solution. It means it's going to be a good solution to the equation. So, you know, kind of keep that in mind. You can short circuit the check process a little bit here if you really want to, in that you can just make sure that you don't get logs of negative numbers anywhere. I'm going to go ahead and try to check this equation and see how it works out. And we're going to have to go to the next page to do that. So what I'm going to do here is I'm going to copy our equation down and go to the next page and then use 12 elevenths to try to check that. Right, so there's my equation, and I want to check x equals 12 elevenths. Right, because remember, that's what we got as our solution on this page here, is we got 12 elevenths as the solution. And again, it may not be the simplest check at all. So you get 12 elevenths, the log of 12 elevenths plus 12, yuck, equals the log of 12 elevenths plus the log of 12. Like so. Right? And so the log of 12 elevenths plus 12, you would actually need to get a common denominator there, which is 11. So you have a log of 12 elevenths plus, and then that's 12 over 1. You're going to multiply that by 11 over 11. That gives you 132 over 11. So you have 132 over 11 right here. And then that would give you the log of 144 over 11. Yuck. On the other side of the equation, you've got the product rule, right? Because it's an addition problem. This is a product rule problem. So you have the log of 12 elevenths times 12. And sure enough, what do you get? You get the log of, just multiply those together because it's 12 over 1. And you get log of 144 over 11. And so it does check. Not, again, not the easiest check in the world by any means, but it does check. All right, so let's see. Let's look at problem number 50 next. First, we'll talk about whether this is a type 1 or a type 2 log equation. So you have log base 3 of 3x minus log base 3 of 6 equals log base 3 of 77. All right, so in this particular equation, this is definitely type 2. Every term is a log term. And so since every term is a log term, we can get this equation in the form logarithm equals a logarithm. To get it in the form log equals a log equals log like this, then we're going to have to combine these two logarithms on the left side of the equation. Right, these two need to be combined. This is a subtraction problem, and so the subtraction problems, remember you use the quotient rule because this is subtraction. To combine those two is one logarithm. So you have logarithm base 3 of 3x over 6, like that. Right? That's the quotient rule for logarithms. Right? The log minus a log means you have the log of a fraction. And then on the right side, you have log base 3 of 77. So what's got to be true here? The 3x over 6. Oh, and by the way, that's just x over 2, and it wasn't paying attention there. But that reduces right here, right? So this is log base 3 of x over 2 equals log base 3 of 77. All right? And so now you have logarithm equals a logarithm, and so the only way that can be true is if you have x over 2 is equal to 77. right? The expressions themselves, the numbers themselves have to be equal. And then you multiply both sides by 2, and you get x is 154. So 154 is our solution. You could check that, certainly. And so you have log base 3 of 3 times 154 minus log base 3 of 6 is supposed to equal log base 3 of 77. So 3 times 154, that 3 times 154 is 462. So you have logarithm base 3 of 462. Yeah, I was making sure that that's right. Minus log base 3 of 6 equals log base 3 of 77. Now you use the quotient rule, and you have log base 3 of 462 over 6. It's supposed to equal log base 3 of 77. And sure enough, when you divide 6 into 462, you do get 77. So you have log base 3 of 77 equals log base 3 of 77. And let me write that a little bit nicer. And so that checks. So 154 is our solution in this equation. Okay. Let's see. Let's look at, so we're doing good, let's look at problem number, let's look at problem number 55. So 55, you have log of 4 plus log of negative 5x equals 2. So now remember, we're trying to decide whether this is a type 1 or a type 2 logarithm equation. In this case, you have a constant term in there, right? This is not a logarithm, this 2 right here. And because you have that constant term, this is going to be a type 1 logarithm equation. And so what do you want with a type 1 logarithm equation? Well, you want logarithm base a of whatever equals a constant. Right? You want a logarithm equals a constant. So this is a problem where we do need to use the product rule to combine these two. Right? This is a product rule problem. And why is it product rule? Because this is addition. Right, and so you get log of, I'm going to use brackets here, 4 times negative 5x, close off the brackets, equals 2. And so you get logarithm of negative 20x is equal to 2. Right, so what has to be true here? Now that you got logarithm equals a constant, you can write this in exponential form, right? This is the log form right here. And you want to now rewrite this in exponential form. Remember that the base on this logarithm is 10 because there's no base written down. So it's always a logarithm equals a constant. You know, I've said that a lot over the last couple of lectures. So a logarithm equals an exponent. So the logarithm is equal to the exponent here. And so that 2 has got to be the exponent. 10 is the base. So you have 10 to the second power is equal to negative 20x. That's our exponential form. So you get 100 equals negative 20x. Divide by negative 20, you get negative 5 as x. Right? And so we get that negative 5 is our solution. If we want to check this, you have log 4 plus log of negative 5 times negative 5, right? And that's supposed to be equal to 2. So let's see what we get. We get log of 4 plus log of 25, right? And that's a product rule problem. So this is log, because it's addition, of 4 times 25. That's log of 100. The base on the logarithm is 10, so it's the power you raise 10 to get 100, right? That, remember, log of 100 is the power you raise 10 to get 100. That's got to be 2. And sure enough, it checks, because that's what we had on the other side of the equation. Right? So, all right, we're doing good, doing good. Problem 64. Problem 64, you have the natural log of x minus the natural log of x plus 3 equals the natural log of 6. All right, so on problem 64, all the terms are logarithm terms, right? No terms that are constant terms in there anywhere. And so this is what we call a type 2 log equation, right? We can get this as a logarithm equals a logarithm. To combine these two logarithms, since it's a subtraction problem, we know that to subtract two logarithms, we use the quotient rule. So this is the natural log of x over x plus 3 equals the natural log of 6. Like that. And now we have logarithm equals a logarithm. So we know that when that's true, that the two numbers themselves have to be equal. And so you have x over x plus 3 is equal to 6. Like that. And then finally, we multiply both sides by x plus 3. To solve this for x, right, the x plus 3 is divided out here, and you get x equals, and on this side of the equation, you have 6x plus 18. You subtract 6x from both sides, you get negative 5x equals 18, and then finally divide by negative 5, and you get x is negative 18 over 5. All right, so now when you try to check this equation, try to check that solution, rather, when you get the natural log of negative 18/5, right? I'm going to take my original equation. Every place I see an x, I'm putting negative 18/5. But wait a minute, you can stop pretty much right now, because notice this first term here is the natural log of negative 18/5. That's a no-no. That can't happen. Remember, you cannot have the log of a negative number. And so let's write that. You cannot have the log of a negative. It's not possible because it's not in the domain for the function. And so negative 18/5 cannot be a solution to this equation. So you have to throw this out. This is an extraneous solution. And so this equation does not have a solution. Right, no solution to this equation. I would just write no solution down when you have a problem like this. Okay. All right, so let's see. Let's look at, to kind of finish this up, so we've looked at a lot of different logarithm equations. Let's look at an application that kind of merges together exponential and logarithm equation kind of things. So this is problem number 67 on the next page. So problem number 67. Problem goes like this. The population of a small town is modeled by the equation P equals 1,650 e to the 0.5 t, where t is measured in years. In approximately how many years will the town's population reach 20,000? In how many years? So when you see those words, by the way, in how many years, you're saying that the time is unknown, right? The time is what we're going to try to find in the problem. Will the population, so that's, when I say the population, that's P. All right, so that's our question. In how many years will the population reach 20,000? So let's talk about this equation for a minute. Exponential functions are common to use when you're modeling population growth. So what's the population now? That's my first question. What's the population now in this problem? The population now would be when t is 0. Right? And so when t is 0, you get p is equal to 1,650 e to the 0.5 times 0 power. So notice that there the exponent is just 0. So you have e to the 0. And so you get 1,650, because e to the 0, remember, is 1. Anything to the 0 power is 1. So the population now is 1,650. That's the present population of this town, is 1,650 people. And this equation models what would project the population to be over time. Sometimes they may try to make projections like this for the future. Sometimes they go backwards, and that's actually typically what happens, is they'll go backwards maybe 10, 20, 30 years, something like that, and they'll try to find an exponential equation that models the population over the last 20 or 30 years, and then assume that that model will continue to be true for a while. Now, what happens is these models only work for a short length of time, and then various different things happen. The economy changes. Also a plant is built close to this town, and so the population grows much faster. A plant closes down close to the town, then the population starts to decline. All sorts of things that go on in cities that make the population ebb and flow and rise faster, rise slower, things like that. So these exponential models only work for a short length of time, and then you have to come up with a different model. So let's say that this is projecting the population out past or into the future here. And so the population now would be 1,650. So the population in 10 years, let's say, that would be when t is 10 in our problem. And so we would take our model and we would substitute 10 in for t. And so you have population is 1,650 times e to the 5th power. And this is where you would bring your calculator into play, and you'd raise e to the 5th power. Remember, to raise e to the 5th power on a graphing calculator, you hit the second key, and then you hit the ln key. And that combination of keys brings up e raised to a power. And then you enter the exponent, and then close the exponent, the parentheses on the exponent. So e to the 5th power is 148. See, 1,650 times 148, like that. And you have 244,881. So the population is 244,881. Now, think about the fact that this model probably is not accurate out to 10 years, because you've got this town right now that has a population of 1,650 people. It'd be kind of unrealistic that in 10 years they would have 250,000 people in 10 years like that. Now, it's possible it could happen if there's some kind of economic boom in the area, but that's not likely to happen. All right. So the question, now to answer the question, the question was, in how many years, so t is the unknown in the problem, will the population reach 20,000? So that would mean that the population is 20,000. And so we get this equation. We have 20,000 equals 1,650 e to the 0.5 t. And this is a type 1 exponential equation. I'm sorry, a type 2 exponential equation, because we would need to use logarithms to solve this equation. So you'd have 20,000 divided by 1,650 equals e to the 0.5 t, like that. And we're going to take the log of both sides of the equation. Now, first thing I'm going to do is I'm going to take 20,000 and divide it by 1,650. And I get 12, I'm going to round this, I'm going to get 12.5 0.12, the 12 actually repeats, equals e to the 0.5t. And then I take the log of both sides of the equation. So you have the log of 12.12 equals the natural log of e to the 0.5t. Now remember, use the natural log here because the base was e on the exponential expression. And when you see the base when you see the base is e on an exponential expression, use the natural log on both sides. So you have the natural log of 12.12 is equal to, use the power rule here, and you get 0.5t times the natural log of e. Don't forget that the natural log of e is equal to 1. So this factor goes away. And so you're left with the natural log of 12.12. Not 12 times 12, it's 12.12 equals 0.5t. So t would be the natural log of 12.12 divided by 0.5. Another problem where you would definitely need to use your calculator to get a decimal for that. And when I use my calculator, I get about 4.989. So about 5 years, right? That's the answer, right? If you're looking at it, it's really close to 5 years. So that would be kind of our answer here, is about 5 years to get to 20,000 people. Means this town is growing pretty fast. Right, so here's my 5 years here. I'm going to bring that up here like that. Right, for it to go from 1,650 people now, and in about 5 years, it's sitting at 20,000 people. This is a fast-growing city. All right, so your homework, your textbook homework, will be on page 535. Page 535. This is on logarithms now, on logarithm equations. This starts at problem 29 and goes 29 through 65 odd. Those would be good practice problems. That's good practice right there. Okay, so now just a little bit of information about the future before we finish up the lecture. So next week is Thanksgiving, but I am going to live lecture on Monday. Campuses across the Lone Star system are open on Monday and Tuesday. So next week, lecture definitely on, let's see, that would be November the 20th. And that's what we're going to do, is move on to systems of equations. So there's a lecture on November the 20th. Online office hours. Will be Sunday, 7:30 to 9. Monday, 8 to 9. Tuesday, 8 to 9. But that's it. No office hours on Wednesday, no office hours on Thursday, or the rest of the week. All right, so no lecture next on November the 22nd. So no lecture November 22nd, which is a week from today, because campuses are closed across the campus, across the system. And then the following week, right, is when we're going to have November the 27th. That's a Monday. We're going to look at matrices and using matrices to solve systems of equations. November 29th is Wednesday. No lecture on that day. I will be on campus on that day. I'll be on campus then, but we're not going to have a lecture on that day at all. And then exam 3 opens November the 30th. Right, and we'll talk more about when I'm going to be on campus and everything as we get closer to that. So we really have very few lectures left to go for the rest of the semester. So the semester is really winding down really quickly. Okay, so everybody have a great day. I hope keep after it and try to finish